Good morning to one and all present here. Today I, Kanishka Meena, and my friends Harsh Gupta, Khushi Sani, Mrutul Mishra, Mukund Verma, and Naina Chivamalani are going to present a PPT on the topic Explanation of Hydrogen Spectrum, Excitation Energy, and Ionization Energy. So, here we start. What is atomic spectra? Atomic spectra is the study of atoms and atomic ions through the interaction with electromagnetic radiation. As the, as the atomic electron energy levels are unique to each element, the lines in a spectrum, known emission or adsorption, can be used to identify the elements present in the source or gas between the source of us. When light travels from one medium to another, it either bends towards the normal or away from the normal. The phenomena of, of various mediums, speed of light, depends upon the nature of medium through which it passes. Next, line spectra. When atoms are excited, they emit light of certain wavelengths, which corresponds to different colors. The emitted light can be observed as a series of colored lines with dark spaces in between. This series of colored lines is called a line or atomic spectra. Each element produces a unique set of spectral lines. There is an intimate connection between the atomic structures of an atom and its spectral characteristics. Atoms of individual elements emit light at only specific wavelengths, producing a light spectrum rather than the continuous spectrum of all wavelengths produced by a hot object. Next, please. Emission spectrum. Whenever electromagnetic radiation interacts with atom and molecules of matter, the electron in these atoms may absorb energy and jump to a higher energy state, losing their stability. In order to regain this stability, they need to move from the higher energy state to the previous lower energy state. To accomplish this job, these atoms and molecules emit radiation in various regions of the electromagnetic spectrum. The spectrum of radiation emitted by the electrons in excited atoms or molecules is known as emission spectrum. Next, adsorption spectrum. When we observe that when a ray of white light falls on a prism, it experiences refraction twice. Once when it travels from a rarer medium to a denser medium, and again from a denser medium to a rarer medium. Finally, we observe a band of colors called spectrum formed by a ray of white light. If we observe the spectrum more closely, the color having a smaller wavelength deviates the most and vice versa. Thus, a spectrum of colors ranging from red to violet is observed where red has the highest, having the longest wavelength, suffers the least deviation. This kind of spectrum is called continuous spectrum as violet merges into blue, blue into green, and so on. Next, adsorption spectrum. Bohr model of the hydrogen atom was the first atomic model to successfully explain the radiation spectra of atomic hydrogen. Niels Bohr introduced the atomic hydrogen model in the year 1930. Bohr model of the hydrogen atom attempts to plug in certain gaps certain gaps suggested by the Ford model. It holds a special place in history as it gave rise to quantum mechanics by introducing the quantum theory. Next, planetary motion model of the atom. Quantum mechanics emerged in the mid 1920s. Niels Bohr, one of the founders of quantum mechanics, was interested in much debated topic of the time, the structure of the atom. Numerous atomic models, including by the theory postulated by J.J. Thomson and the discovery of nucleus by Ernest Rutherford had emerged, but Bohr supported the planetary model which asserted that electrons revolved around a positively charged nucleus, just like the planets around the sun. Next, Now I would like to call my friend Harsh Gupta for the further PPT. Thank you.
Thank you, Kanishka. Now my topic is Bohr's equation. Bohr model of the hydrogen atom first proposed the planetary model, but later an assumption concerning the electrons was made. The assumption was the quantization of the structure of atoms. Bohr proposed that electrons orbited the nucleus in specific orbits or shells with a fixed radius. Only those shells with a radius provided by the equation below were allowed, and it was possible for electrons to exist between these shells. The Bohr's radius for a value of r is equal to 0.5 to 9 × 10⁻⁻⁻⁷ Bohr also calculated the energy of an electron in the nth level of hydrogen by considering the electrons in circular quantized orbits as E is equals to minus 1 upon n square into 13.6 electron volt, where 13.6 electron volt is the lowest possible energy of a hydrogen electron. Next, please. Bohr's radius. The diameter of the hydrogen atom for stationary states is r is equals to 4 pi epsilon naught n square h square upon me square, which is equals to n square a naught, where the Bohr radius is given by the following equation given below. The smallest diameter of the hydrogen atom is 2r1 is equals to 2a naught, which is almost equals to 10 raised to power minus 10 meter. For n is equals to 1 gives its lowest energy state, also called the ground state. Next, please. Adsorption and emission. According to Bohr's model, an electron would adsorb energy in the form of photons to get excited to a higher energy level. After exciting to a higher energy level, also known as the excited state, the excited electrons is less stable. The energy of the emitted photon is equal to the difference in energy between the two energy levels for a specific transition. The energy can be calculated using the equation h mu is equals to delta E, which is equals to 1 upon n n2 minus 1 upon n square high into 13.6 electron volt, as we can see in this figure. Next, please. Now my friend Mridul Mishra will explain the further slides.
Thank you, Harsh, for inviting me. Postulates of Bohr model. In an atom, electrons, which are negatively charged particles, revolve around the positively charged particle's nucleus in a definite circular path called as orbits or shells. Second, each orbit or shell has a fixed energy, and these circular orbits are known as orbital shells. Third, the energy levels are represented by an integer, where n equals to 1, 2, 3, and so on, known as the quantum number. This range of quantum number starts from nucleus side with n equals to 1 having the lowest energy level. The orbits n equals to 1, 2, 3, 4, and so on are assigned as k, l, m, n respectively shells, and when an electron attains the lowest energy level, it is said to be in the ground state. Fourth, the electrons in an atom move from lower energy level to a higher energy level by gaining the required energy, and an electron moves from a higher energy level to a lower energy level by losing energy. Next slide, please. De Broglie's comment on Bohr's second postulate. De Broglie came up with an explanation for why the angular momentum might be quantized in the manner Bohr assumed it was. De Broglie realized that if you use the wavelength associated with the electron and assume that an integral multiple of wavelengths must fit in the circumference of an orbit, you get the same quantized angular momenta that Bohr did. The circumference of the circular orbit must be an integral multiple or number of wavelengths, which is 2 pi r equals to n pi, which is equals to nh upon pi, where h is the Planck's constant. The momentum p is simply mv as long as we are talking about non-relativistic relativistic speed. So this becomes 2 pi r equals to nh upon mv. Rearranging this a little gives the relationship IR equals to MVR, which is equals to NH upon 2 pi. Next slide, please. Limitation of Bohr model for hydrogen atom. First, Bohr's model doesn't work well for complex atoms. Second, it couldn't explain why some spectral lines are more intense than others. Third, it could not explain why some spectral lines split into multiple lines in the presence of a magnetic field. Fourth, the Heisenberg's uncertainty principle contradicts Bohr's idea of electrons existing in a specific orbits with a known radius and velocity. Next slide, please. Bohr's energy level. Different orbits in which electrons revolve are known as stationary states or energy level. These stationary states or energy level for an electron are numbered as n equals to 1, 2, 3, and so on. These integers are also known as the principal quantum number. Energy of the stationary state in which an electron is placed is given by En, where n is the stationary state number, is equals to minus Rh into 1 upon n square, where Rh is also called as Rydberg's constant, whose value is 2.18 into 10 to the power minus 18 joules. Next PPT, please. Ground state and excited state. A ground state atom is an atom in which the total energy of electrons cannot be lowered by transferring one or more electrons to different orbitals. That is, in a ground state atom, all electrons are in the lowest possible energy level. An excited state of a system, such as an atom, molecule, or nucleus, is any quantum state of an system that has higher energy than the ground state, that is, more energy than the absolute minimum. Excitation is an elevation in energy level above an arbitrary baseline energy state. Next slide, please. Now, I would like to invite Mukund to explain the further PPT.
Thank you,
Thank you.
Mridul, for inviting me. Now the topic is ionization energy. Ionization energy is the energy needed to remove an electron from an atom in the gaseous state. Second, the first ionization energy is the energy needed to remove the first electron from the atom in the gaseous state. Second ionization energy is the energy needed to remove the second electron from the atom in the gaseous state. Next slide please. Factors governing the ionization energy. First, if the nucleus is positively charged, then the electrons are strongly attracted to it. Second, if an electron lies near or close to the nucleus, then the attraction will be greater than the one when the electron is further away. Third, if there are more electrons between the outer level and the nucleus, the attraction force are less. Fourth, when there are two electrons in the same orbital, they experience some from repulsion. Now, this creates the disturbance in the attraction of the nucleus, and hence ionization energy will be less in paired electrons as they can be removed easily. Next slide, please. Now, the further slides will be explained by Nana.
Thank you, Mukund, for inviting me. Excitation energy. Excitation energy is the addition of a discrete amount of energy to a system, such as an atomic nucleus, an atom, or a molecule that results in its alteration, ordinarily from the condition of lowest energy, that is ground state, to one of the higher energy excited state. The excitation energy of an energy state is the difference between the energy of the excited state and that of the ground state. For example, for the hydrogen atom, the ground state energy of the first orbit is E1 is equals to minus 13.6 electron volt, and energy of the second orbit is E2 is equals to minus 3.4 electron volt. Next slide, please. Hydrogen spectrum. Electrons in an atom or a molecule absorb energy and get excited. They jump from a lower energy level to a higher energy level, and they emit radiation when they come back to their original states. This phenomenon accounts for the emission spectrum through hydrogen 2, better known as the hydrogen emission spectrum. The hydrogen spectrum is an important piece of evidence to show the quantized electron structure of an atom. The hydrogen emission spectrum comprises radiation of discrete frequencies. These series of radiation are named after the scientists who discovered them. Next slide, please. When a hydrogen atom absorbs a photon, it causes the electron to experience a transition to a higher energy level. For example, n is equals to 1 to n is equals to 2. When a photon is emitted through a hydrogen atom, the electron undergoes a transition from a higher energy level to a lower. For example, n is equals to 3 to n is equals to 2. During this transition from a higher energy level to a lower energy level, there is a transmission of light occurs. The quantized energy levels of the atoms cause the spectrum to comprise wavelengths that reflect the differences in these energy levels. For example, the line at 656 nanometer corresponds to the transition at n is equals to 3 to n is equals to 2. Now I would like to call Kushi Sani for the further slides.
हो गया कंप्लीट